Before we plunge into the declaration, understanding what is significant, molecule gas pedals are the enormous Hadron Collider LHC, work by CERN. It is a 17 ring of superconducting magnets and the world's biggest and most powerful atom smasher. It represents the zenith of human scientific achievement. Truth be told, it's so powerful that it can reproduce the very states of the universe's introduction to the world. Yet, could this machine, intended to unlock the mysteries of the universe, hold the key to something far more foreboding? CERN, established in 1954, is one of the world's most prestigious research organizations, with 23 member states and thousands of scientists. It is a hub for collaboration and innovation. The LHC is CERN's flagship project, yet it's only one part of a vast network of accelerators and experiments. Envision a racetrack, not for vehicles or horses, but for subatomic particles in a race against time and space itself. The LHC accelerates protons to nearly the speed of light, sending them on a collision course that mimics the energy of the universe at the moment of the Big Bang. These collisions create temperatures millions of times hotter than the core of the Sun. Thousands of magnets guide the protons on their journey, while complex cooling systems keep the magnets at temperatures colder than space. The beams inside the LHC are made to collide at 4 locations around the accelerator ring, corresponding to the positions of 4 particle detectors: Atlas, CMS, ALICE, and LHCb. Each serves a unique purpose, investigating different aspects of particle physics. Together, they act as enormous cameras, capturing snapshots of these collisions. Scientists then sift through the debris, searching for signs of the elusive Higgs boson, also known as the God particle, and other phenomena that offer clues to the fundamental structure of the universe. By studying the microcosm, we gain insights into the cosmos. However, with each answer comes another question, and with each discovery, another challenge. The LHC isn't just a scientific instrument. It's a testament to human curiosity and innovation. It embodies our relentless pursuit of knowledge and our desire to understand the fundamental forces that shape our universe. Yet, as we push the boundaries of what we know, we must also consider the ethical and existential questions that arise. What are the risks of probing the unknown? Could our quest for understanding unintentionally unleash forces beyond our control? In the sacred halls of CERN, where the limits of human comprehension are constantly tested, a revelation has emerged, one that sends a shiver down the spine of even the most seasoned scientists. Brian Cox, a former scientist at CERN and a leading voice in particle physics, recently made a declaration that has left the world both fascinated and fearful. His words resonate with haunting clarity. The goal of CERN's Large Hadron Collider is to recreate a miniature Big Bang. Yes, you heard that right, a small-scale version of the very event that gave birth to our universe. The physicist went on to explain the implications of this goal, highlighting the LHC's exceptional potential for groundbreaking discoveries. This includes its ability to unlock the secrets of the Higgs boson and explore dark matter, a mysterious substance that makes up a significant portion of the universe. Imagine holding the power of creation in your hands, the ability to summon the very essence of the universe. It's a tantalizing prospect, but one fraught with danger. The Little Big Bang is not just a theoretical concept. It is a tangible reality within the LHC. The temperatures, the pressures, the raw energy, all replicate the conditions of the universe's earliest moments. It is as if we are standing at the very beginning, witnessing the birth of existence itself. However, with such power comes responsibility, and the question looms: what if something goes wrong? In truth, something did go wrong back in 1978. The Russian physicist Anatoly Bugorsky experienced a catastrophe that would forever alter the course of his life. While working on the U-70 synchrotron at the Institute for High-Energy Physics in Protvino, Russia, a malfunction led to his head accidentally coming into direct contact with a proton beam. The beam, so powerful that it defies comprehension, passed through his skull, entering the back of his head and exiting through his nose. Bugorsky's experience was astonishing. He saw a flash brighter than 1,000 suns, yet he felt no pain. The beam's path left a trail of destruction, burning tissue and bone. Yet he remained conscious and even walked to the clinic for treatment. The outcome was both horrifying and fascinating. The beam caused localized tissue death, leading to partial facial paralysis and hearing loss in one ear. However, incredibly, Bugorsky's cognitive abilities remained intact, and he continued his scientific career. This incident is not just a personal tragedy, but a cautionary tale, one that highlights the immense power and potential dangers of particle accelerators. The risks of an atom smasher like the LHC should not be taken lightly. The potential for unforeseen reactions, the manipulation of the very fabric of existence. These are not the stuff of science fiction, but real concerns voiced by some in the scientific community. One of the most unsettling and captivating concerns surrounding the LHC's experiments is the possibility of creating a miniature black hole. Black holes are regions of space-time where gravity is so strong that not even light can escape. They are cosmic vacuum cleaners, devourers of stars, enigmatic entities lurking in the shadows of our universe. The idea that the LHC could create such an entity, even on a microscopic scale, is shocking to both the public and experts alike. Could such a black hole grow uncontrollably, consuming the Earth from within? Scientists at CERN assure us that any black hole created would be unstable and would vanish almost instantly. However, the mere possibility has sparked debates, fears, and awe at the power we wield. It is crucial to understand how the LHC could potentially create a black hole. It all comes down to the fundamental mechanics of particle accelerators. When protons collide at nearly the speed of light, the energy released is so immense that it distorts the fabric of spacetime itself. Imagine a trampoline stretched tight, then dropping a heavy object onto it. The fabric bends and warps. If the weight is heavy enough, it could create a depression so deep that anything nearby would be pulled into it. This is a simplified analogy for what could happen in the LHC. In the realm of quantum physics, where the laws of the universe are both strange and beautiful, there exists a theory that additional dimensions may be hidden within our reality. If these dimensions exist, the LHC's collisions could tap into them, creating a gravitational funnel that forms a microscopic black hole. This enigmatic dance of particles even captured the attention of world-renowned scientists, particularly the late Stephen Hawking. In his work, he warned of a scenario in which the Higgs boson could become unstable at extremely high energy levels. This instability could trigger a catastrophic vacuum decay, an event that would not only destroy Earth, but could also annihilate the entire universe. The esteemed British cosmologist and astrophysicist Sir Martin Rees also voiced his own concerns about the experiments conducted at CERN. In his book on the future, Prospects for Humanity, the scientists at CERN have conducted extensive calculations, run countless simulations, and examined every theoretical framework to ensure the safety of the LHC. Brian Cox himself has acknowledged the significance of responsible scientific exploration. Recognizing the widespread fears surrounding the LHC's experiments, he has emphasized that rigorous safety measures, extensive peer reviews, and strict protocols are in place to ensure that the collider operates with utmost caution. Cox reassures that the energy levels involved in the LHC's collisions are well within the natural conditions that Earth has encountered throughout its history. Cosmic rays, high-energy particles originating from space, have been bombarding our planet for billions of years, producing similar or even higher energy collisions than those occurring inside the LHC. Yet, Earth remains intact. Furthermore, even if a microscopic black hole were to form, scientists argue that it would be so minuscule and so unstable that it would evaporate almost instantly. This phenomenon, known as Hawking radiation, was predicted by Stephen Hawking and suggests that tiny black holes lose mass and vanish almost immediately in a burst of energy. Despite these scientific assurances, fears persist. Some theorists have speculated that the LHC's experiments could tear the fabric of spacetime, opening a doorway to another dimension or parallel universe. This notion, while largely dismissed by mainstream physicists, has captured the imagination of many and has been the subject of widespread speculation, conspiracy theories, and even science fiction narratives. Could the LHC's collisions create a rift in reality, unleashing forces beyond our comprehension? Some point to the strange anomalies reported around CERN, unusual magnetic fluctuations, unexplained particle detections, and even bizarre occurrences in the surrounding areas. To skeptics, these are mere coincidences or misinterpretations of data. To others, they hint at something more mysterious, something CERN itself may not fully understand. Then, there is the question of the unknown. Science, at its core, is an exploration of the mysteries of existence. But with each discovery, we are forced to confront new and often unsettling realities. The LHC is not just a machine, it is a gateway to the deepest and most fundamental questions about our universe. What is reality made of? What forces govern our existence? And, perhaps most chillingly, are we prepared for the answers we might find? The pursuit of knowledge is humanity's greatest strength, but it also comes with immense responsibility. As we push the boundaries of science further than ever before, we must ask ourselves, are we unlocking the secrets of the cosmos, or tampering with forces we barely understand? Perhaps only time will tell. The idea of extra dimensions isn't new in physics. String theory, a leading candidate for a unified theory of everything, suggests that there may be more than the familiar three dimensions of space and one of time. These extra dimensions could be compactified or hidden from our perception, but they could theoretically be accessed or revealed under extreme conditions. Now, imagine the Large Hadron Collider, LHC, as a cosmic key, unlocking doors that have been sealed since the earliest days of recorded history. When protons collide at energies never before achieved on Earth, they could, in theory, create ripples or tears in the fabric of space-time. These tears could open pathways to dimensions beyond our own, like cracks in an enormous wall that separates us from the unknown. The consequences would be like dropping a stone into a perfectly still lake. The impact creates waves and ripples that spread out, interacting with everything they touch. In the case of the LHC, those waves could be disturbances in the dimensions themselves, waves that spread out into realms we cannot see or comprehend. Scientists at CERN are quick to point out that the energies required to create such a portal are likely far beyond what the LHC can achieve. The idea of opening a doorway to another dimension remains firmly in the realm of science fiction. However, the very fact that we can contemplate such possibilities, explore the boundaries of our understanding, and peer into the void of the unknown is a testament to the power of human curiosity and creativity. For the scientists at CERN, it should serve as a silent warning. Some doors, once opened, may reveal truths we are not ready to face. Scientific, legal, and ethical questions. The LHC's experiments have not only raised scientific and philosophical questions, but also legal and ethical ones. The very act of recreating the conditions of the birth of the universe, of reaching into the primordial soup of existence and stirring it with our technological spoons, has sparked debates that transcend the boundaries of science. Are we playing God? Are we stepping onto sacred ground, meddling with forces that were once solely the domain of the universe? These are not just rhetorical questions, but profoundly unsettling inquiries that challenge our very understanding of ethics and responsibility. The creation of a miniature black hole, for example, is not merely a scientific curiosity, but a potential Pandora's box. Imagine a whirlpool sucking everything into its inescapable grasp, but on a cosmic scale. Some legal scholars and ethicists have questioned whether humanity has the right to take such risks, even in the pursuit of knowledge. Lawsuits have been filed seeking to halt the LHC's experiments, citing concerns about safety and the potential for catastrophic consequences. The debates rage on, not just in courts but in academia, the media, and around dinner tables. In 2008, a lawsuit was filed in Hawaii by Walter Wagner and Luis Sancho, who sought to stop the LHC's operations. They argued that the collider could produce planet-devouring black holes, or previously unknown phenomena that could destroy not just Earth, but the entire universe. The lawsuit demanded a temporary restraining order against CERN, claiming the organization had failed to provide an environmental impact statement as required by U.S. law. Although the case was dismissed, it ignited a firestorm of debate and brought the LHC's potential risks into sharp focus. Across the Atlantic, in Germany, a professor named Otto Rosseler filed a complaint with the European Court of Human Rights, asserting that the LHC violated the right to life guaranteed by the European Convention on Human Rights. Rosseler's concerns were rooted in the fear that the LHC could create microscopic black holes that might grow uncontrollably. Though both lawsuits ultimately failed, they were part of a broader movement of skepticism and concern surrounding the LHC. They reflected a deep-seated anxiety about the unknown, a fear that our pursuit of knowledge could lead us down a path of no return. CERN, born from the ashes of war. CERN was founded in the aftermath of World War II, when the world was still recovering, and the echoes of destruction were a grim reminder of human folly. It was a time when the very fabric of civilization had been torn apart. From that chaos, a group of visionary scientists dared to dream. They envisioned a place where national boundaries would dissolve, where the pursuit of knowledge would be a beacon of hope. They imagined a laboratory, a crucible where the mysteries of the universe could be explored and the secrets of existence unlocked. Thus, CERN was born, a child of war and wisdom, a symbol of what humanity could achieve when driven by curiosity rather than conflict. Over the years, CERN has been at the forefront of particle physics, contributing to our understanding of the fundamental forces and particles that make up the universe. The organization has been involved in numerous groundbreaking discoveries, such as the discovery of neutral currents and the W and Z bosons, which mediate the weak nuclear force. The discovery of the Higgs boson, a particle that gives mass to other particles. For decades, the Higgs boson was a theoretical ghost, a whispered legend in the halls of physics. Its existence was a puzzle that teased scientists, a question wrapped in the very fabric of reality. CERN's relentless pursuit of this elusive particle led to a moment that shook the scientific world. In 2012, the Large Hadron Collider finally uncovered the God particle. It was a triumph of human ingenuity, a testament to our insatiable hunger for knowledge. New discoveries and the expanding universe of particle physics. The Higgs boson is not the only mystery being investigated at CERN. Scientists have made astonishing breakthroughs, including the discovery of a particle that challenges our conventional understanding of physics, the pentaquark. As its name suggests, the pentaquark consists of 5 quarks, including an antiquark. This is a significant departure from the more familiar protons and neutrons, which are composed of only 3 quarks each. The existence of such a particle was not expected in nature, making its discovery a testament to the unpredictable and often bewildering nature of the quantum world. The discovery of the pentaquark at the Large Hadron Collider in Switzerland has opened a new frontier in our understanding of the universe. These particles may exist for only a trillionth of a billionth of a billionth of a second, but their implications could be eternal. They could hold the key to understanding how the universe is formed, how fundamental particles stay together, how the strong nuclear force, the glue holding atomic nuclei together, operates. The pentaquark is not alone in its exoticism. Alongside it, scientists have discovered new tetraquark particles, composed of 4 quarks. These discoveries are not merely adding to the particle zoo. They are redefining our understanding of matter. They are allowing scientists to classify these particles, much like elements in the periodic table, paving the way for a new theory governing exotic matter. Moreover, in May 2023, CERN scientists made another major breakthrough: the observation of a rare Higgs boson decay into 2 muons, a crucial step in confirming the Higgs boson's properties. In April 2023, CERN announced the discovery of a new particle, smaller than quarks and leptons, challenging our current